Okay, class, let's move on to chapter 11, which will be dealing with bending. Okay, and there's a strong correlation between the centroid and the kind of bending that you will experience in certain types of beams, depending on the load that's being applied. And I explain a little further, but when it comes to bending, we're really evaluating or analyzing beams. And beams typically are just members that are slender and that support a loading that typically is applied perpendicular to the longitudinal axis. Okay, so now there are various types of um, supports, or I should say, beams are supported in various ways. For instance, a beam can be supported through a cantilever. You can have what you know as a simply supported beam. You can have what you know as an overhanging beam because the supports are right here and the beam is hanging over. Excuse me, the supports. And then you have what you know as a continuous type of beam, right? You have fixed end. So these are some of the variations of the types of beams that we would encounter. And when we go in terms of application, I mean, beams are used in different ways. I mean, you see here that this beam almost serves as a crane, which is used to pick up other beams in this particular factory. You can see here that we have these different types of beams that are used to hold up this structure. Likewise here, you've probably seen this in different malls where you have these beams horizontally or in a perpendicular fashion be able to hold this glass in position. Okay, it's something that we kind of normally come across every day. We see this pole here, which is really nothing more than a beam that has to hold these traffic lights at certain locations, and has to also withstand wind and other kinds of environmental weather conditions. Okay, now the type of load that a beam will experience. Okay, um, there are various types. Okay, you have what you know as a concentrated load. This more like a pointed. It's right at the point of that beam along that beam. You have what you know as a uniform distributed load, where the load is just uniform across the whole beam itself. Okay, and these are your supports. And you have what you know as a varying load because it's more like in a triangular formation. Okay, call that triangular load. Triangular load. I'm sorry, but it's varying from this end to this end. Okay, and then you have what you know as applied couple, where you're applying a moment across this particular beam. So, but the idea is really is the reason why we're going through this and this exercise is we want to be able to know how or what are the shear forces, internal shear forces that these beams experience when you have these loads on, when you have these various types of loads on top of them, right? We also want to know how they're going to bend as well, because that will determine the type of material you choose, what type of loading conditions will be applicable. So this information is very useful when it comes to designing beams for various applications. You definitely don't want to um, use a beam that is not suitable for a particular application because it will be catastrophic. Okay, so let's look at an example. So we have this example here whereby we have a beam at A and at B, right? And we have a load, a pointed load, right, of 9 kips. Okay, and it has, and I'm going to show you the long way and I'm going to show you the short way. It's going to be 8 feet and 4 feet here. Okay, so the idea is really we want to be able to develop the shear force, the maximum shear force, and the maximum bending moment for this particular beam. And as we learned in class, you got to find your free body diagram. So if you draw your free body diagram, this is your AY, and this is going to be your BY. And of course, since it's a pin here, you're going to have two forces acting on it, AX and AY. But of course, your AX is going to go to 0 because there are no forces in the X direction. Looking at this beam. So in order to find what our AY and BY is, we can use our equilibrium equations. We can say sum of the moments about point A. So let me just finish this off. You have 9K here, and then you have 8 feet and 4 feet. Okay. Sum of the moments about point A equals 0. Okay, so this is my point of interest here. So it's going to be 9K by 8 feet minus BY by 12. Okay, equals 0. So our BY happens to be 72 divided by 12. 9 times 8 divided by 12 equals 6. Okay, so that's going to be 6 kips. Okay, then we could take some of the moments about point B equals 0. It's a point of interest here. We're going to have negative 9 kips by 4 plus AY by 12 equals 0. And that's typically going to be 36 divided by 12, and that's going to be AY. It's going to be 3. Okay, so we found our support reactions, and you know that AX is going to equal 0. But that comes from the sum of the forces in the X direction equals 0. Therefore, your AX equals 0. Okay, so I'm just going to erase this part right here. So we can have our space. Okay, just something bigger. Okay, so for step number 1, we've drawn our free body diagram. We found our support reactions. Um, so BY happens to be 6, and AY happens to be 3. Okay. Okay, so now let's move forward, and we want to be able to draw our shear force diagram. Okay, and in doing so, what we can do is we're just going to extend this line. Okay, and we are going to just draw a horizontal line. It's going to be our shear line, and this is going to be 0 line right here, and this is going to be in kips. Okay. Now the idea is here we're going to do this graphically. So our support reaction is going upward, right? So the idea is now we want to move from, this is our 0 line, we go up by 3 kips. This is 3 kips right here. Then we go over horizontally till we get to this 9 kips. It pushes us down to 0. Then we go 6 more. There's 6 kips right here below the 0. Then we go over. And then we have a support reaction, BY, of 6 kips going in the up direction, right? So we go back up here. Okay. So that's what you see right here. Okay. So this is your graph of your shear force. Okay. Now I'm going to extend this line a little bit more here. Okay. And I'm going to draw another line. And this is my moment line. And this is also a 0 line. And that's going to be kips feet. Okay. Now the idea is I should be able to find the area of this shape here. So we know this is from here to here is 8 feet, and it has a height of 24. I mean, have a height of 3. So that's 24, right? 24 kips foot. So when you want to translate this geometric shape on the moment diagram, it's going to be a straight line like this. Okay? So here's going to be 24. Now, as you notice that this particular geometric shape is below the 0 line, so, and it also has an area of 6 by 4. This is 4, okay, which is 24. So what that does is it brings it back down to 0, okay? So your maximum bended moment, as we call it, capital M subscript um, max equals 24 kip feet. And this is going to be your answer right here. Okay? The answer here is going to be the maximum shear force is going to be 6. Okay? So I hope this helps. Let's do another problem. Okay? So when you do this particular problem, we are, let me just write here the solution. First thing you want to do is you want to be able to draw your free body diagram. Okay? And then this is going to be your AY, AX, okay? This is your BY, okay? And then we have our two forces acting down. This is 12K. This is 8K, okay? And then we're going to, has a span, looking at 5 feet, okay? 4 feet, and then 3 feet, okay? So, but we need to find out what AY is and what BY is. Those are support reactions. That's our step number 2, right? So we can come here and say sum of the moments about point A equals 0. I'm taking clockwise to be positive. I'm going to get 12 by 5 plus 8 kips by 9 feet, right? Minus BY times 12 feet equals 0. Okay, when I solve for BY, I'm going to get 11 kips. Okay, when I take the moments, so this right here is going to be 11 kips. The sum of the moments about point B equals 0. This is my point of interest. So the distance, this force, 8 kips, is separated by a distance of 3 feet. Okay, so I have this force, 8 kips. It comes in contact with a perpendicular distance of 3 feet. So when they come in contact with each other, this force wants to rotate this way, which is against what I just proposed earlier. I told you that my moment is going to be positive in a clockwise. Well, this moment is going to behave in a counterclockwise. So that's going to be a negative. So in doing so, we're going to get a negative 8 kips by 3 feet. Okay. And then same thing here. My 12 kips over 7 feet. Okay. Plus my AY. This is my AY. It's a force here. And that has a span from the point of interest. And that's going to be 12 feet equals 0. Then my AY happens to be 9 kips. This is 9 kips. So I'm just going to erase this part right here. Okay. Okay, now that we found our support reactions, we want to take this a step further. Okay. And now what we can do now is we can actually, this is going to be our shear force line. Okay. Again, the units are going to be in kips, and this is going to be a 0 line. Okay. And now what we do here is we notice our support reaction AY goes up 9 kips. So this is 9 kips here. And we go over, because there's no force between the support reaction and the next pointed load here. So we just go over. Once we get to this 12 kips, we have to respect it, in other words. So we had 9 kips, but we have 12 kips, so it's going to bring us down to 3 kips. 12 minus 9 gives us 3, but that's below the 0 line here. So then we go over again. We have another 8 kips. It brings us further down. That brings us to 11 kips. Then we go over. Then we have a support reaction that's going up 11 kips. It takes us back to 0. Okay, so this is going to be above the shear force um, diagram, and this is below the shear force diagram. Okay, now we want to be able to draw our moment, bending moment. Okay, and that's going to be kips feet. Okay, so I'm going to use a different color. So here it's positive, it's above the 0 line, right? So again, whenever we want to translate our shear force into our bending moment diagram, you're taking the area under this of this geometric shape, and this is 5 feet by 9 kips. That's going to give us 45, and that's going to be a slanted line like this. It's going to be 45. Okay, now this particular geometric shape is 3 by 4, which is 3 times 4 is 12. Okay, and we subtract that from 45, right? That gives us 33. This is 33 right here. Now this geometric shape here is 11 by 3. Okay, 11 by 3 is 33, and that brings us back to 0. Okay, so you can see here that um, this will be your maximum bending moment, happens to be 45 kips feet. Okay, let's let me stop here, and come up with I'll continue with the next video. Okay, I hope this helps. Thank you.